Hello, welcome everyone. Today's lecture, we are going to look at another example of combined loading of a circular shaft. And the reason that we do two examples of this type is because this is one of the most important class of problems that you will actually learn in this course. And that is very important when you go and design shafts in your 342 class, which is the design class. Okay, so what are we trying to do here? We are essentially trying to do what we did in the previous lectures, which is essentially to analyze the state of stress in a shaft that is subjected to combined loading. The shaft has a circular cross-section, and we are essentially interested in two things. Finding out what is the maximum bending or normal stress that this shaft experiences due to this combined loading, and the maximum shear stress that this shaft experiences because of combined loading. And we are also interested in finding out what is the precise location in the shaft where you have this maximum bending stress or normal stress and the maximum shear stress. Okay, so we will try to go through this example a little bit faster because last time we went through step by step. So this time we'll go a little bit faster. Okay, so again, this is the shaft that you're looking at here. So we have a shaft that goes from A to B. Okay, it is a circular shaft and it has a diameter of 1 inch. Okay, and it's also given that the shaft is supported at points A here and point B here. So essentially what that means is that you are only going to have only two force reactions at point A and point B. There are going to be no moment reactions, and there's going to be no force reaction along the axial direction. So along the x-axis here, you are not going to have any reaction force at point A and point B. Okay, and we also provided a bunch of forces that are actually acting on the shaft. So if you look at point C here, which is 3 inches from point A, you have a force of 417 pounds that is acting in the minus Z direction. Okay, similarly at point D here, you have two forces, one acting along the minus Z direction or the plus Z direction of 217 pounds, and you have a force that is acting in the minus Y direction of 125 pounds. Okay, so these are the forces that are acting on the shaft. Apart from that, you also have two moments acting on the shaft. So there is a moment of 1000 pound-inches, okay, and that moment is along the x direction. So it is going to be a torque. Similarly, at point D, you have another torque of 1000 pound-inches, but in the opposite direction. So these two externally applied torques cancel out each other, so there is moment equilibrium there. Okay, so these are the external forces and moments that are acting on this particular shaft. So typically what you would be given is actually a shaft with a gear or a pulley on it, and then you'll have forces acting on the gear and the pulley, and that you will reduce into a diagram like this, or a free body diagram like this. But in this case, we are just looking at a specific example where we know all the forces and the moments that are already acting on the shaft, and we are interested in finding out which point in the shaft or which points in the shaft have the maximum tensile and compressive normal stress, and which points have the maximum shear stress. Okay, so for any problem like this, okay, when you're given a structure and you're asked to find out the maximum stress or the maximum deformation, the first thing you have to do is find out the reactions. So here we are going to have two reactions at point A. Those are going to be the forces in the y direction AY and the force in the z direction AZ. Similarly, if you look at point B, which is the other point where the shaft is actually supported, you have a BY and a BZ. Okay, and the reason that we only have these two forces, as I mentioned earlier, is because the shaft is simply supported. Okay, so first we have to find out AY, AZ, and BZ and BY. Okay, but we also have to kind of keep in mind what the coordinate system is. So here the coordinate system is defined such that the x-axis is along the axis of the shaft. It goes from A to B. The z-axis is vertical, and the y-axis is going to the right. Okay, so this is the coordinate system that we have to work with, something that you have to keep in mind. Okay, so let's just look at the way we are going to find out the reactions at A and B. So the first thing is do force equilibrium. So AZ plus BZ should be equal to the net force in the z direction, and that is 200 pounds. Similarly, AY plus BY should be equal to the net force in the y direction, and that is 125 pounds, because the 125 pound force is actually acting in the minus y direction. Okay, and remember, we have assumed all our reactions, AY and By and Az and Bz to be in the positive y and the positive z direction. Okay, and this is just an assumption. We don't know for sure that they're going to turn out to be positive or negative. Once we solve the equations and find out Az, Bz, and so on, we'll find out whether the assumed directions are correct or not. Okay. Now, that is your force equilibrium equations. So then you can also look at the moment equilibrium. So you can again do moment equilibrium about any point. In this case, I'm taking the sum of moments along the z direction about the point A. And essentially, there are only two things or two forces that contribute to this moment. So that is the 125 pound force here and the By, the reaction at B. Okay, so if you do that, you find out what By is. That turns out to be 90.3 pounds. And then using this equation here, Ay plus By is 125 pounds, you can find out what Ay is. And Ay turns out to be 34.7 pounds. Okay, so that's how you find Ay and By. Remember, this moment here, 1000 pounds here and here, those are moments along the x direction. So they don't contribute to My or Mz. Okay, those are essentially torques. Okay, so again, you can do the same thing for moment equilibrium along the y-axis, about the y-axis. And again, I'm doing moment equilibrium about the point A. And here we have contribution from three forces, the 417 pound force here, the 217 pound force here, and Bz. Okay, Az of course doesn't contribute because it is about, we are taking the moment about point A. Okay, and again, if you do the calculations here, you find out that Bz is minus 87.2 pounds and Az is 287.2 pounds. So what does it mean? Bz is in the direction opposite to what we have assumed. So we have assumed that Bz is in the positive z direction, but actually it turns out that Bc is in the negative z direction, and the magnitude of Bz is 87.2 pounds. On the other hand, Az is in the assumed direction, and the value of Az is 287.2 pounds. So this is the first step. So essentially, the first thing you do is find out all the required reactions, all the reactions that are going to be present in all the supports in the particular problem. Okay. Once you draw, once you find out the support reactions, then the next thing is to draw the free body diagram and then draw your shear and moment diagram and your torque diagram. And that's exactly what we're going to do next. Okay. So first we're going to look at the torque diagram because it's fairly easy in this particular case. So if you look at this shaft here, you essentially have two torques of 1000 pounds in this direction here, okay, and the opposite direction here. Okay. So the first thing you do when you want to construct a torque diagram is to find out what is the direction of these external torques. So, and that essentially is what I have done here. So if you look at this point C here, okay, you use your right hand rule. So my fingers are curling along the direction of the torque there, here, this one, okay? And if I do that, you can see that my right thumb is pointing in the left direction. So that is why the torque at point C is pointing to the left, okay? So that is an external torque, okay? And the value of the torque is of course 1000 pound-inches, okay? The torque at point D, the external torque that is applied at point D, again, if you use the right hand rule, you do this, your fingers are curling this way, now the thumb is pointing to the right, and that is why you have it pointing to the right here, okay? So just because you need to have equilibrium, the torques at point C and point D have to be in the opposite direction because there are no external or no internal torques, no torques at the two supports, okay? At point A and point B, there are no reaction torques. So which means that the externally applied torques have to essentially cancel off each other. So that's why they are in the opposite direction. Okay. Once you know what is the direction of the external torques at point C and point D, it is clear that for any point between A and C here, the internal torque is 0. Because if you take a section between A and C, the external torque is 0, which means the internal torque also has to be 0. Similarly, for the point for the segment of the shaft between D and B, the internal torque has to be 0 because there are no external torques there. So A to C is 0 and D to B is also 0. Okay. Now, if you take a section between C and D though, you have an internal torque. Okay. And what you do is you take a section between C and D. That is what I have done here. And then if you look at the free body diagram here, you have the torque Tc that is pointing to the left, which means that the torque, internal torque TCD has to be pointing to the right. Okay, so that is why it is pointing to the right here. Okay, and the value of TCD has to be equal to TC, and that is going to be 1000 pound-inches. Okay, now the question is whether this TCD is a positive internal torque or a negative internal torque. Okay, and the way you determine that is you put your hand along the direction, or you look at the direction of the torque here, the internal torque that is pointing to the right, and the outward normal to the surface is also pointing to the right. So if the internal torque and the outward normal to the surface point in the same direction, then that internal torque is considered positive. On the other hand, if TCD was pointing to the left, then it would be considered negative. So in this case, TCD is positive. Okay, and you can look at any section between C and D, it wouldn't matter, and you will find that the internal torque at any point between C and D is going to be positive, and it is going to have a value of 1000 pound-inches. The torque diagram here, it jumps to 1000 pounds at point C, 1000 pound-inches at point C, and stays there, and then comes down to 0 at point D. Okay, that is why the torque diagram looks the way as it is drawn here. Okay, so that is the simplest part. So the torque here, you have only two external torques, and you only have internal torque between those 2 points C and D. Okay, and again, I want to remind you that this torque that I'm talking about is basically the moment about the x direction, or the moment about the axis of the shaft. That is why I have also mentioned that it is mx here. Okay, so that essentially takes care of the internal torque part of this problem. Okay, the next thing, of course, you have to do is look at the shear and moment diagrams. Okay, now in this case, you have forces in two different directions, like AY are in the z direction and the y direction, which means that you essentially have to draw the shear and moment diagrams in two different planes. Okay, so first what we are going to do is we are going to consider the xz plane. Okay, so that is what I'm doing here. So we are going to look at the xz plane, okay, draw the free body diagram for the forces that are acting in the xz plane, and based on that, draw the shear and moment diagrams. Okay, so if you look at the xz plane, you have a reaction 287.2 pounds at point A. You have a reaction at point B that is in the minus z direction. Okay, that is 87.2 pounds. And you also have two external forces, 417 pounds here and 217 pounds there. Okay, so but with finding AZ and BZ, we essentially know all the forces that are acting on the xz plane. And once you have this free body diagram, it's fairly easy to construct the shear force diagram that I have done here. So it is going to be Vz, because the forces, the internal shear forces, are going to be in the z direction. Okay, now this is something that you have done many times, so it is not something that I need to explain. If you have this kind of a free body diagram, so you have a positive force of 287.2 pounds at point A, so the shear diagram jumps, okay, and goes to 287.2, and then at point C it comes down by 417, then it stays constant, then at this point it goes up by 217, and then it stays constant, and then at this point it comes down by 87.2. Okay, and that is why you have this kind of a shear force diagram. Okay, and this is something that you have done multiple times, both in this class and also in your solid mechanics class, so it's not something very difficult. Okay, now once you construct the shear diagram, you can use the shear diagram to construct the moment diagram, and that is what we are going to do next. Okay, so if you look at the shear diagram here, you basically, to start with, it's constant, which means that the slope of the moment diagram is going to be constant and positive. Then here, again, the shear force is positive but negative, so which means that the slope of the moment diagram is going to be negative. And then this segment here from D to B, again you have a positive value of shear, which means that the slope of the moment diagram is going to be positive. So, and based on that, if you draw the moment diagram, it essentially looks like that. Okay, so it's positive first, then negative, then positive, the slope. Okay, and of course, based on the slope, you can actually calculate what the values of the moment at these points are. Okay, it turns out to be 861.6 at point C, and this point, let me just write this down here, this point corresponds to C, and that point corresponds to D. This is of course A, and that is B. Okay, so that is how your moment diagram looks like. Okay, now what you have learned in the previous lectures is that you can draw the moment diagram as you did in your solid mechanics class, but then in this class we have to make sure that the sign of the moment diagram is correct. Okay, and for that, essentially what you do is you take a section at any point along the shaft, draw the free body diagram, and find the direction of the internal moment, and see whether the sign of the internal moment that you get from the free body diagram matches with the sign of the internal moment that you get from the bending moment diagram. If the signs are the same, it means that your bending moment diagram is correct as it is. If they are opposite, then essentially you have to flip the sign of your bending moment diagram. So in this case, that is what I have done. I have taken some section between point A and point C, and if you do that, this is your reaction force at point A. So there has to be a shear force of 287.2 at this point here, at the section that you're taking, and you must have an internal moment going in that particular direction to counter the rotation due to this force here. Okay, so that moment value has to be 287.2 times x, which is the distance. Okay, but here we are not so much interested in the value of the moment, but rather at the sign of the moment. So the main thing that to notice is that the direction of the moment has to be my, has to be in this direction. And if you use your right hand rule now, if I curl my fingers along the direction of the moment, what you see is that my thumb is pointing towards me, which is in the positive y direction. Okay, so in this case, this is your x, that is your z, and that is your y. Okay, so in this case, if you use your right hand rule and put your fingers this way, then the right thumb is going to point in the positive y direction, which means that the moment my is positive in this particular segment. Okay, and what you know is that from this diagram here, okay, the moment is positive between any point between A and C. So what it tells you is that the direction of the moment that you obtain from the free body diagram and the moment that you obtain from the bending moment diagram, they essentially have the same sign, which means that you can leave the bending moment diagram as it is. So it is good as it is. So you don't have to do anything else. Okay. So that's something that you must do in every step. So every time you construct a bending moment diagram in this class, just make sure that the bending moment diagram is actually has the right sense. Okay, that is something that you must keep in mind. Okay. So now we have found that the bending moment diagram as you have done for my is correct. So now we are going to repeat the same process for the xy plane. Okay, so in the xy plane, it's a little bit simpler. You essentially have only one external force. Okay, and based on that, you can construct your shear force diagram. It is going to be very simple. It's going to be a straight line all the way from point A to point D. Okay, and from point D to B, it is going to be negative. It is going to have a jump downwards of 125 pounds here. Okay, that is the force that you have at this point, right? And then it's going to remain constant from D to B. Okay, so that is how the shear force diagram looks like for this particular case. Okay, and once you have the shear force diagram, you can construct the bending moment diagram. Now, here I want to kind of emphasize two things. The first thing is that this is Vy, okay, because we are operating in the xy plane. So the shear has to be in the y direction. On the other hand, the moment is in the z direction. So if you're looking at forces in the xy plane, the moment necessarily have to be in the z direction. So that is something that you must keep in mind. So in the previous case, it was the xz plane, so the moment was in the y direction. So now it is xy plane, so the moment is in the z direction. Okay. Now, we already have the shear force diagram as it is here. Okay, and from that, if you construct the moment diagram, it will essentially look like this, because your shear is positive from A to point D, okay, which means that the slope of the moment has to be positive. Okay, now if you do that, you will essentially have a diagram that looks like this. Okay, that goes up from A to D and then goes down from D to B. Okay, now is that the correct diagram? Okay, for that we have to check using our free body diagram. So how are you going to do that? Again, the same thing. You take any point between A and D here, okay, and then take a section. Okay, so now what you know is that you have a reaction force of 34.7 pounds there, which means that you are going to have a moment mz in that direction, okay, to counteract the rotation of the force at point A. So it's in this direction. Now, if you curl your fingers this way now, my right thumb is pointing towards me, okay? But look at the direction of z here. Z is pointing inwards, which is opposite to the direction of the thumb here, which means that this bending moment mz is actually negative. On the other hand, my bending moment diagram tells me that it's going to be positive, okay? Which means that I have to flip the sign. So the bending moment direction that you get from the free body diagram is the correct one. So if the bending moment that you get from the bending moment diagram disagrees with that, you essentially have to flip the bending moment diagram. So essentially, even though this is what you might get from like applying the principles that you used in 213 or your solid mechanics class, in this class, because we are more worried about the sign, you have to make sure that the bending moment diagram is flipped, and this is the correct bending moment diagram. Okay, so I'm just going to erase these things, but you kind of get the picture. So this here is the correct bending moment diagram. Okay, something that you must keep in mind. So in some cases, it's obvious that the bending moment diagram that we draw and the bending moment that you're going to get from the free body diagram is going to be the same. But in some cases, it is not quite obvious. And the reason that we have to flip this particular diagram here is because this coordinate system that is provided here, okay, is not, in some sense, a regular right-handed coordinate system. So if you do a right-handed coordinate system, the z would be pointing out. But in this particular case, the z is pointing in. Okay, so it is more like a z-y-x coordinate system rather than an x-y-z coordinate system. Okay, and that is the reason why you have to essentially flip the sign here. Okay, but the reason that we are doing this is because once we are consistent with the coordinate system that are given here, then it's very easy to figure out which particular points are going to be in compression and which particular points are going to be in tension at any given cross section. Okay. Okay. So now what we have done is we have constructed the my and mz diagram. We have made sure that their signs are correct, and now the point is to find out where the resultant moment is maximum. Okay. So we know my and mz as a function of x. Now we have to find out mr as a function of x. Okay. So again, this is something that we went through in the previous class. If you have a bending moment diagram where all segments are linear, then you essentially have to examine the mr only at the critical point. So if you look at the my diagram here, okay, so there are 2 points. This is A and this is B and this is point C and this is point D. Okay, so essentially the my diagram changes slope at 2 points, point C and point D. So we have to look at those particular points because those are the critical points. Similarly, if you look at the bending moment diagram for the z direction, you have 1 point here, which is point D, where you have a change in slope. Okay, so we have to look at the point D. So if you look at both my and mz, we essentially have 2 critical points where you have to evaluate mr, which is point C and point D. Okay, so those are the 2 points where you can have the maximum mr in this particular case. Okay, there is no other point that we have to really look at. On the other hand, if the bending moment diagrams were not completely linear, so there was a quadratic segment or a cubic segment, then we essentially have to find mr as a function of x and then maximize or minimize mr. Okay, but in cases where the bending moment diagrams are linear, it is much simpler. We just have to look at the critical points. Okay, so now we know that the critical points are point C and point D. So we evaluate MR at point D and point C. Okay, so MR at point D is fairly straightforward. We already know what the values are. It's 436 and 451, right? You put those values in, take the square root, and then you essentially get MR at D to be 627.36 pound inches. Okay. Now, for the point at C, it is just a little bit more complicated because we know one of the values already. So let me just erase this. So we know that the My at point C is 861.6, but we don't know what is the value of Mz at point C. So essentially, if you look at some point here, we know that the point C is 3 inches from point A, okay, and the slope of this is 34.7, okay, which means that the Mz at C is going to be 34.7 times 3, which is 104.1. Okay, that's it. Very simple. So it's minus 104.1 because it's in the negative direction. Okay, and once you know what is the Mz at C, you already know what My at C is. You just find out Mr, and that turns out to be 861.86 pound inches. Again, in this case, it is very obvious that the location C is going to have the maximum resultant moment because Mz or My at C is really large, 861.6 pound inches. Okay, so we know that the maximum stressed point is going to be at the cross section at C. Okay, so again, I want you to kind of think about this carefully. All that you have done so far is find out the point where the internal resultant moment is maximum. We still don't know what specific point within that cross section is going to have the maximum bending stress, and that is what we'll do next. Okay, but right now we know what is the maximum internal moment is going to be for the entire shaft, that is at point C. Okay, and I also kind of want to go back to the torque diagram and show you that both at point C and point D you have the maximum torque. Okay, so it looks like you're going to also have the maximum shear stress or torsional shear stress occurring at the cross section at C. Okay, actually it's going to occur at every cross section between C and D, but C also turns out to be the point where you have the maximum internal moment. Okay. Okay, so we have done all this. So now once we know which cross section has the maximum internal resultant moment, we essentially use this formula. Sigma is MC over I. So where this M is nothing but your MR. Okay, so that is the 867.86 number here. This is 0.5 inches because the diameter is given to be 1 inch. So the radius is going to be 0.5 inches. And of course, this is your I. So that is pi c to the 4 divided by 4. Okay, and if you make the calculation, it turns out that the maximum internal maximum bending stress at the cross section C is going to be 8.84 pounds per square inch. That is KSI. Okay, and you can also find out what the maximum shear stress is. This is nothing but TC over J. The maximum torque we know is 1000 pound inches. C is again 0.5. J is now pi times 0.5 to the 4 divided by 2. And if you do that calculation, you find out that the maximum shear stress is going to be 5.09 pounds per square inch. So this maximum shear stress is going to occur at every point along the circumference of the shaft. Okay, and it is going to occur at every location starting from point C here, point C here to point D. So at every point, at every cross section between C and D, the internal torque is 1000 pound inches, and in that every cross section of those, along all the points along the circumference, you are going to have the maximum shear stress. Okay, but the bending stress is different. So if you look at the bending stress, we know that it is maximum at point C because that is where you have the maximum resultant moment, internal resultant moment, right? So the shear stress is going to be maximum at many points, but the bending stress is going to be maximum only at 1 or 2 points. Okay, so how do you find out what those 2 points are? That is where we essentially have to take a cross section at point C and then look at the cross section here. Okay, so if you look at the cross section here, your Z is pointing up, okay, and we are looking at it from this angle here. Okay, so we are looking at it from that particular angle. So z is pointing up, y is pointing to the left, and your x-axis, most importantly, is coming out. Okay, it is coming towards you. Okay, that is something that is given. So the reason that I'm so particular about this is because we draw our bending moment diagrams, my and mz, as a function of x. So we always assume that when you're drawing the bending moment or when you're plotting the my and mz, the bending moment is plotted for a cross-section whose normal is the positive x-axis. Okay, so that is why we have to look at a cross-section whose normal is the positive x-axis. Okay, it is for that section we know what the bending moments are, my and mz. So if you go back, we found that the my is positive at point C, it is 861.6, and mz is negative and it is minus 104.1. So using those two, essentially you can figure out that my is 861.6 this way, mz is going to be negative, so it's in the opposite direction to the positive z direction. That is why it is pointing downwards. It's 104.1. Okay, and once you know my and mz, you can find out what this theta is. Okay, theta is going to be nothing but my divided by mz, and the sorry, I made a mistake here. So this essentially means that theta is 83.1 degrees. Okay, so tan theta is 861.6 by 104.1, which means that your theta is going to be 83.1. Okay, so that essentially tells you what is the direction of mr. Okay, now we know something more, because for a circular cross-section, the direction of mr coincides with the direction of the neutral axis. Okay, so this is going to be your neutral axis. Okay, so if that is going to be neutral axis, then the points that are farthest from the neutral axis, which is going to be point P and point Q, okay, those are going to have the maximum bending stresses. Okay, so here we know what is the direction of mr, that is provided by theta. We know that aligns with the neutral axis, which means that the points P and Q, which are perpendicular, which is essentially the perpendicular diameter to the neutral axis, they are going to have the maximum stresses. Okay, now how do you know whether point P is going to be under compression or tension? For that, we again use your right hand rule. So you point your thumb along the direction of mr, and what you see is that your fingers will be pressing point P. So if it is pressing, it is compressive. So point P is going to be under compression, and the diametrically opposite point, which is Q, is going to be under tension. Okay? So point P is going to be having a stress of minus 8.84 pounds per square inch, kilopounds per square inch. The point Q is going to have a tensile bending stress of 8.84 kilopounds per square inch. Okay? And of course, both these points P and Q are going to have the maximum shear stress because they are both at the circumference. Okay? So effectively, if you look at this problem, we first narrowed down where the resultant bending moment is maximum. Then we figured out where the resultant or internal torque is maximum. It so happens that at point C, or the location C, you have the maximum internal torque and also maximum resultant bending moment. So we know that the maximum stress point in this particular shaft has to lie at the cross-section at point C. Okay? And once we know that information, we can zoom in and figure out exactly which point within that cross-section is going to have the maximum bending stress, which is going to be, in this case, point P and point Q. One is going to have maximum, going to have a tensile bending stress, other is going to have a compressive bending stress, and we know exactly how to find those. Okay? I hope this particular problem kind of reinforced some of the things that we learned in the last class, and these kinds of problems are very important for your shaft design in your machine design class, which is going to be the one that follows this particular class. So if you're comfortable with drawing shear and moment diagrams with the correct sign, and then being able to figure out which points are going to have the maximum tensile and compressive stresses, which points are going to have the maximum shear stresses, then your design becomes much simpler. Okay. With that, I'll conclude and I'll see you in the next lecture. Thank you.